Good morning, students. Today we shall learn about a very new chapter of mathematics, that is complex numbers and quadratic equations. And before we start, let us talk about why we have this chapter complex numbers in class 11th. What is the need of this complex number? If you go back to class 10th standard and try to memorize the chapter quadratic equations, what exactly you have done there? While finding the roots of the given equations by the quadratic formula, we first find out d, which is nothing but discriminant, given as b square minus 4ac. And based on the value of discriminant, we used to analyze whether the given quadratic equations will be having equal roots or distinct roots or real roots or non-real roots, right? So the case third, when we have d less than 0, the value of discriminant less than 0, in that case we used to write the given equation has got imaginary roots or non-real roots, right? Because the value less than 0 will be negative, all right? And the formula which we were using was alpha and beta, which is given as minus b plus square root of d by 2a and minus b minus square root of d by 2a. So when d is negative, the value of a square root of a negative number was impossible there. So that was the need of complex numbers, okay? So we have till now, so far we have studied about real numbers, we have studied about rationals and irrationals, natural, whole numbers, and integers. But in class 11th, we'll talk about complex numbers. By looking at one example here, x squared plus 1 equals to 0. What is the value of x? So value of x is given as minus 1 here, and x becomes a square root of minus 1. So x equals to a square root of minus 1 is not a real number. This becomes the complex number. We'll read about this particular thing a little more in detail in the later part of this chapter. Let's understand the equations and the introductions of the given chapter, complex numbers. Complex numbers are the numbers of the form x plus iy, where I is equals to a square root of minus 1, and x and y are the real numbers. I is also called as iota, which is a Greek term. So x and y are the real numbers, but we have the divisions here. We'll talk about the division also. Complex numbers are defined as the ordered pair of real numbers like x and y, where z is equals to xy and represented as x plus iy, where x is the real z, rez, and iy is called as imz, imaginary z, okay? X and y are the real numbers. X is known as real part, complex numbers, and y is known as imaginary part of the complex numbers. We also write that as real z equals to x and imaginary z equals to y, which I have just discussed here. Two complex numbers. Let's take an example. Z1 equals to a plus ib, or z2 equals to c plus id. We can also write it as a plus bi. That's fine. All right. So these two complex numbers can be said to be equal only in one condition, that is if a equals to c, the real parts are equal as well as the imaginary part are also equal, then in that case we call z1 equals to z2. Some examples with the values here. Z1 equals to 2 plus 4i, where z1 also equals to 8 minus 4i. Simply we can write z equals to 2 plus 4i, that is also fine, or 2 plus i4, that is also fine. Algebra of complex numbers. Just like real numbers, addition, subtraction, multiplication, and division is also performed on complex numbers. So addition of complex number is the first topic here. So let z1 equals to x1 plus iy1 and z2 equals to x2 plus iy2. Then addition of z1 plus z2 will give you x1 plus x2, together all the real part, and I, which is common, y1 plus y2. I hope you know how it is performed here. If you write simply x1 plus I y1 plus x2 plus I y2, you take x1 and x2 together, the real part, and if you take I common, it will be y1 plus y2. Therefore, real part of both the complex numbers are added, and similarly, imaginary part of both the complex numbers are also added. Addition of complex numbers also follows the closure commutative associative laws that we have seen already in our previous number systems. In natural numbers, in integers, we have read about these particular terms in the properties of additions, subtraction, multiplication, and division. We have seen how closure property works, how commutative associative laws, as well as the additive identity, which was 0, if you try to recollect your things, and then complex numbers. And additive inverse also exists for the complex numbers, where z, which is imaginary complex number, given as x plus iy, additive inverse is written as minus x minus iy. So plus becomes minus here, right? So additive inverse of plus 2 we have seen as minus 2. Remember, the addition of the given complex number as well as its additive inverse will always give you 0. We'll discuss more about these complex number examples in the virtual class with more verification way. We'll verify each and every property here, like what is closure property. So I'll just give you a little bit of information regarding what these properties means. Just to revise it, closure means when we add two complex numbers in complex number cases, the result is always the complex numbers. In commutative, additions of any two complex numbers in any order is possible. In associative laws, we take three complex numbers and addition in any order is also possible. So closure means what? If I have two complex numbers z1 plus z2, the result is z3. This is also the complex number. In case of commutative, we have z1 plus z2 equals to z2 plus z1. In any order it is possible. Similarly for associative also. And for additive identity, if you add 0 to any complex number, the identity is same. Okay, it will remains the same. It will be z1 only. If you add 1 plus 0, the result is 1 only. In the same manner, z plus 0 will give you z only. In case of additive inverse, if you just put z, suppose I'm writing z equals to a plus ib. So what is inverse of z? Minus z. So it will be minus a plus ib. So the result is minus a minus ib. Okay, this is like minus x minus iy. The second operation is subtraction of complex number. So the two complex numbers z1 minus z2 will give you x1 minus x2 plus I y1 minus y2. So the real part is subtracted first and then the imaginary part separately. The properties of subtraction is not valid here. It is not closed under closure, commutative, associative, because you might get different results. Like in natural number case, 2 minus 3 equals to, it's not equal to 3 minus 2. Both will give you the different results. You can try out by taking some more examples based on subtraction or complex number. Try to verify whether it is closure, commutative, associative or not. And then we can see the later part of this particular chapter in our next class. That's all from today. Thank you.